Okay, so last time we were talking about, or we ended up talking about eigenvectors and eigenvalues of a particular set of equations. We were interested in the matrix on one side. And it turned out that it was degenerate, so it had the eigenvalue of 1 twice. So I reformulated that problem not to worry so much about the degenerate value, which is actually kind of a pathological case. But we can take the same system of equations and address it a little simpler. And I wanted to go through that to start out. And then I have some climate-related stuff to talk about because it's Friday. So we'll have some climate things, thinking about linearity and the scaling of response to forcing, whether that works in the climate problem, which will touch on some of the ideas that will lead us toward differential equations. Because you'll see, even from that sort of brief discussion, that things are not simultaneous in time in the Earth system response to forcing. And so we'll start to think about how that fits together a little. So that'll be seeds for future discussion. But let's start with the eigenvalues discussion first. So we had a standard matrix A, B, C, D, and then our particular set of equations was x plus y and y equals 2 equals 3. And so we had written that as a matrix system, which was what, 1, 1, 0, 1 equals 2, 3, or xy equals 2, 3. Here's the change I'm going to make that's going to make our eigenvalue life easier. I'm just going to multiply this equation by 2. It doesn't change the meaning at all. But it's
6, right?
Yeah, sorry. It's a funny looking 6. Okay, so the matrix version of that then is what? One, 1, 0, 2, x, y, 2, 6. Okay? So, is this matrix invertible?
Yes.
Yes. All right, how did you check it? You checked it by calculating the determinant, which was this one times this one minus this one times this one. So the determinant is 2. Okay. How did we, and so we talked about getting the eigenvalues out of a matrix. How did we do that? If we wanted to get the eigenvalues out of this matrix, how would we do it? Remember we had this funny thing where we said matrix minus an eigenvalue, I'm going to use lambda so I don't get confused because that's what I use in the notes, times the identity matrix. And that was supposed to be acting on our eigenvector, and we can put a little I on it. This reminds us that this one is the same one, corresponds to that one, equals 0. And that's just a rewriting of our basic eigenvector relationship. It looks like this. So what's the use? Why do we want to have these eigenvectors and eigenvalues anyway? Aside from the fact that they're just an object. What do we talk about as being useful? We're going to close on another concept that it's really useful about. But does anybody remember?
Maybe this is wrong. Can't you create a new kind of set of axes using the eigenvectors?
We can create a new set of axes, and we can create a special representation of the M matrix that makes it simpler. But last class, we talked about the much simpler idea just of these things don't commute. Maybe we want something that commutes. This side does commute because it's just a scalar. So this is the same thing as this, right? I can put it on either side I want because it's a scalar. And in fact, writing it on this side will actually be useful when we get to that specialized form of writing the matrix using the eigenvalues and eigenvectors. Okay. So what did we do with this thing? We wanted to use this equation somehow to generate the eigenvalues. And there was a particular line of argument that we went through that allowed us to convert calculating the determinant of this object to specify the eigenvalues. What was that? Yeah.
Nope, never mind, wrong.
Okay. So we just played this game where we said this is invertible, and so we could invert it and put it on the other side, and then we would know what x and y were. But last time we said, what if this was, rather than 2 and 6, if it was 0 and 0? If this matrix is invertible, then what's x and y? If I could write it like this, what are x and y if that's true?
0.
There's 0. Because this whole side is 0 if I can do that. So remember, this is the homogeneous system when it's equal to 0. This is the inhomogeneous system where it's not equal to 0. So look, this is a homogeneous system. But we wanted to avoid this circumstance. So how do we avoid this? Because we don't want all the eigenvectors to be 0. We want them to be something interesting. So how do we avoid it? We need to avoid being able to take the inverse. How do we avoid taking the inverse? The determinant is 0. Not the determinant of the original matrix, but the determinant of this funny combination matrix. So we want to evaluate the determinant of A minus lambda B C D minus lambda. And that was what kind of an equation? So it's A minus lambda times D minus lambda minus BC. And if we set that equal to 0, which means that we can't invert this thing, which means that maybe the eigenvectors are non-zero, that gives us a condition. This is the characteristic equation. Characteristic equation is the eigenequation. The word eigen comes from this equation. This is the critical one. What kind of an equation is this? I could write it out this way, lambda squared. If I can do it, last time I couldn't do it. What kind of an equation is that for lambda? It's a quadratic equation. So we can write down the general solution for what the eigenvalues are for a 2 by 2 matrix anyway. It's just the solution to this quadratic equation. So lambda equals A plus D plus or minus, and so they're going to be 2 different roots, 2 different eigenvalues, plus or minus the square root thing. So the square root is going to be B squared minus 4 times A, which is 1, C is this guy. But look, this has an AD, and this thing squared would also have an AD, so there's some cancellation. So it's easier to write it the way that I do in the notes, which is A minus D squared plus 4BC. So it would have been A plus D squared, but then minus 4 times AD. If you multiply that out, it flips the cross term and it makes the plus into a minus. So there's some simplification there. Everybody see what I'm talking about? Okay, so then what are the eigenvalues of our matrix? A plus D, 3, plus or minus A minus D squared, the square root of 1 plus 4 times BC. So I claim that is it's either 1 or 2. Everybody on board with that? Okay, so how can I find the eigenvector now? I've got the eigenvalues set. How can I find the eigenvector?
You
I could plug one of those in and see what happens. Solve for that system. I could also use the formula, which for a 2 by 2 matrix is not that terribly complicated, which is given in the notes. So for the 2 by 2 matrix case, you can just write everything down. There's a quadratic. You can solve the quadratic. You can actually solve the problem in general for the ABCD matrix. So if you don't want to go through all the steps, it's easy to write it down. And actually, you can do it for a 3 by 3 matrix too, and still write down the answers, and it is possible. It's really messy. If you try to do it for a 4 by 4 matrix, it's insanely messy. For a 5 by 5 matrix, it's totally insanely messy. But this method still works for all sizes of matrices. You'll get a characteristic equation. What order will the characteristic equation be? So the 2 by 2 gave us a quadratic. The 3 by 3, what would it give us? We'd have a lambda here and a lambda in the middle and a lambda down there. It'd be a cubic. 4 by 4 would be a quartic, a quintic, and so on. So we might have to use something like Newton's method and fancy root finding if we had like a million by million matrix. But we could do it, and we actually have already had to talk about the tools to do it through Taylor series and all that mess. It exists.
Is that where you can start just breaking it up into separate polynomials?
Yeah, so you could try factoring this.
Yeah.
I mean, here it actually almost is closer to being factored. In some of them, you could probably do factoring. If you were sitting with Mathematica, it would be trivial. It would probably factor all of them. You can't factor it in general because this is arbitrary, this is arbitrary, this is arbitrary. So this is kind of, there's no simplifications. But in any practical application, it would simplify a lot probably because a lot of the terms would vanish.
Okay.
And you could certainly use Newton's method even if it didn't, because we know the polynomials are just going to be wiggly things and you're just looking for where they cross the zero axis. So you could plot the polynomial and do it approximately by just pulling out the locations of the zero crossings on that plot too. That would also be fine. Yeah, so lots of different computational methods. The algebraic methods get complicated beyond 2 by 2. But 2 by 2 we can just write it down. Okay, but let's think about this process. So, our matrix, 1, 1, 0, 2. And now I'm going to write, I don't know, let's write it as u and v, because it's going to be our special eigenvalues. It's not just going to be a general x and y. It's going to be 1 times u and v. We're going to look for the first eigenvector that goes with the first eigenvalue, which is 1. So all I'm doing is rewriting this equation, but plugging in for number 1. Okay, so what's this side? The top row is
U plus V.
u plus v equals u. And the second one, 2v equals v. So where do we start now? This is maybe the easiest one. What's a number for which that's true? 0. Any other number, it's not going to work. So v is going to be 0. And then if v is 0, what's u? Anything it wants to be. So this is one of the tricks about eigenvectors, is their amplitude is arbitrary. You will always get a kind of circular argument. You can renormalize them to any multiple of themselves, and this equation will still hold. If I if I double its size, I double its size on both sides. If I quadruple its size, I quadruple its size on both sides. So I can't possibly find that. So I can normalize it however I want, but let's just write it down. That we say for lambda equals 1, then v equals 1, 0. Because why not pick it to be 1? That's the one. The important thing was that 0 was 0. All right, what about the other one? So now I want to solve this equation. What my system of equations looks like: u plus v equals 2 times u this time, and 2v equals 2v this time. So the second equation is not very useful, except it tells us it's not 0 this time. It's just something.
Couldn't it still be 0, or?
It could still be 0, but it could also be any other number. This time, over here, when it was 2v equals v, it had to be 0. Now it could be anything it wants to be. So let's just try it. What if we, since the size doesn't matter, what if we pick v equals 1? And find the u that goes along with that. So if we say v equals 1, then what do we get? Oh, I'm writing on the wrong side of the line. Oh well. All right. Then u equals what? U plus 1 equals 2u. So, sorry. U 1 equals u. Yeah. Okay. So the other one, lambda equals 2, implies v equals 1, v2, 1, 1. And again, the amplitude of this doesn't matter, so we could say 1/2, 1/2, or we could say 10, 10, or we could say, but they have to be equal to each other. I'll erase this to prove that, to secretly pretend that I never crossed the line. Okay. All right, so that's the process for how you find the eigenvectors. This is how you find the eigenvalues. Once you got them, it's pretty straightforward just to plug and chug and figure out what the eigenvectors are that go along with them. Or you can just look up, use the eigenvector formulas that we have for a 2x2. So why do we care about these things? That's maybe the most important part, which we haven't talked too much. I've just said, hey, look, wouldn't it be cool if we have this equation? So let me show you what's the most powerful general thing we can do. Let's write it down in the explicit version. Okay, in this matrix equation, we have a 2x2 thing multiplied by a 1x2 thing equals a scalar times a 1x2 thing. So like this column goes to that row and that row, right? Just matrix shapes. That's what this equation looks like. I said we could move this to the other side if we wanted to. We can. Okay. What? In fact, I could actually be even fancier and make this a matrix, which has that lambda on the first value and all zeros everywhere else. Does that shape work, sort of? It doesn't, right? I could have just one row with a lambda in the first one. Does that work? This one, no, not quite. I want to write this as a matrix though, and I can do it. What else can I do if I have two eigenvectors and they both have this shape? This is a 2x1, and instead I want it to be a 2x2, say, because then I could multiply times another thing that's 2x2. What if I just write the eigenvectors side by side? Put the other one here. So this is v1, and this is v2. And then what am I going to get on this side? Well, this column goes to this and this, which is the first column of that. So I better write the same thing with v1 and v2 as columns on this side. So that when I do this one, bing, bing, it corresponds to this one. And when I do this one, bing, bing, it corresponds to this one. Looking good, except I've forgotten one thing. What's missing? These are the eigenvectors mapping through the matrix onto themselves. That's part of this system, but what's missing? The eigenvalues. So now, if we do this one will smoothly chug along, multiplying only the first one. This one will chug along, moving only the second one. So this matrix times this is the equivalent of this. This times this is the equivalent of this for both eigenvectors at the same time. Does that make sense? It's just kind of stacking the matrices together. We're still thinking kind of independently of this system with that eigenvalue, this system with that eigenvalue, but this is a way of building it. But look at what we've just written down. This is M times some eigenvector matrix, so let's call it, well, I call it C in the notes, so I'll call it C here, equals the same matrix times that funny one with the lambdas on the axis. And the same thing would have been true if I had a 3x3 or a 4x4. I could have just kept stacking them next to each other until I got a square matrix for C. Yeah?
Could you do an example of what you're showing an example of what you're doing with the?
Yeah, let's write it out. Let's write it out exactly for the one we just had. Sorry. 1, 1, 0, 2 times our two eigenvectors were 0, 1, 0, and 1, 1 equals 1, 0, 1, 1, 1, 2, 0, 0. So that's the one example we just had. Oh, except, yes, that's right. So if I do this, I get 1 up there, which is 1 up there. Then 0, 2, I get 0, 0. On that one, I get 0, 0. On this one, I get 1 plus 1 is 2. On this one, I get 0, 2. On this one, I get 1 plus 2. On this one, I get 0 plus 2. No, I said it wrong, but I did it right on this side. So it works in all four. And so this is one eigenvector. This is one eigenvector, and here it is again on the other side. So this is our C matrix. This is our funny matrix with the lambdas on the diagonal, and zeros off diagonal. And this is our original matrix. Okay? And so, without going into all the detail about the eigenvectors acting as a basis set and all this stuff, which is things you would do in a full linear algebra class, look at this simple thing. If I can invert C, which it turns out you're guaranteed that you can, because of the way that eigenvectors work, I can write that system as C inverse times M times C equals a diagonal matrix. So sometimes this is called diagonalizing the matrix. I took an original matrix, I put it in the space of the eigenvectors. All right, that's a weird thing to think. The eigenvectors, there are lots of them. There are just as many as there are the dimensionality of the whole space. And what we're doing with this multiplication is we're transforming from the original x, y, z coordinates into one that's labeled like direction of one eigenvector, direction of the other. So everything here I'm dotting into that space. And when I do that, I actually end up with a diagonal matrix. So, not to get too fancy, this is a coordinate transformation from the original coordinate system into one that is the natural one for this matrix. It's natural because everybody's on the diagonal. So in this fancy coordinate system, the action of the matrix is just multiplication by a scalar. So if I, said x here, 0 is all the way down, that would be just multiplying x times whichever lambda, whichever place it was in. And so I could solve complicated sets of equations with just scalar multiplication. Once I've switched into this funny space. Yeah.
The C is the eigen.
It's the eigenvector matrix. It's C for columns of that matrix are the eigenvectors. So let's look back at this system, the original system we had, and think about how we might do something with that. So I had m times xy equals 2, 6. But I could multiply m times c inverse times x, y. I haven't done anything, I just multiplied by c times c inverse. And then I could multiply this side times c inverse, this side times c inverse, 2, 6. All right, that looks kind of ugly. But this thing is diagonal. This thing, once I know what c inverse is my input. This is my thing I'm solving for, and this is the forcing. So once I have changed my 2 and 6 into that funny new coordinate system, which is what multiplying by this c inverse does, once I change my x and y into this new coordinate system, I can solve that set of equations just by dividing by the eigenvalues one at a time. Okay? So it's almost like we solve the set of equations for free. Okay, that's all really subtle. What does this actually look like? It looks like we've written equations that have like x plus, well, I can tell you exactly what it looks like if I think about it. So C is that 0, 1, 1, 1 times xy. So I have x plus y. Oh, sorry, can't do it because that's not C inverse. Never mind. I'm not going to write it out. I'm just going to explain it. This is sort of like a different way to solve the set of equations. Because once I have this thing, and I knew what, and I make this multiplication, I'm actually got decoupled equations. So in our present set, xy equals 2y equals 6. What's hard about them is that y appears in both equations. They're coupled. I have to first sort out what y is before I can figure out what x is. But if I had this set, you would tell me that that was really easy to solve. When I'm in this form, the equations are decoupled. Every combination here is detangled from all the other combinations. So I have just multiplication by a scalar equals a constant. Now the thing that I'm multiplying is a different thing than the one I started with. It's not y, it's some combination that comes from C inverse, and the forcing is also some other thing. But this, because this is diagonal, this system is totally decoupled. So, yeah? Yes?
I guess I'm kind of confused about how this equation here on the bottom relates to like the earlier one where we were talking about, where we wrote out the eigen. I guess I'm confused about the relationship between the two, because we have like C inverse MC equals
Yeah.
lambda.
So
So
how did I get there?
yeah,
So
how do you get from like what we were doing earlier to this?
So here's the original equation, and what I did was I inserted into the gap C times C inverse, which is just the identity matrix. So I can stick that in anywhere I like. So I just stuck it in, And then I multiplied on this side by C inverse. And I had to multiply by C inverse on the other side of the equation to keep that straight. And then, after doing those two steps, which I'm totally free to do, just algebra, I then reinterpreted to say, hey, look, here's C inverse times our solution, and here's C inverse times our forcing, and here is a diagonal matrix. So it's why you would do that isn't obvious, except once you're here, looking at this system tells you that you're a long way along. Yeah?
In practice, is like solving a system like this more efficient than doing like a row echelon reduction?
So there's one particular case where it's really important. So if I just take the matrix inverse, it's obviously easier. I had to generate both these eigenvector matrices and also the eigenvalues, et cetera, to get chugging away. But something magic happens here, which is, without using too much time, to leave for homework, the determinant AD minus BC is equal to the product of the eigenvalues. That's always true. So when the matrix inverse fails us, so the determinant is 0, one of the eigenvalues, at least one, has to be 0. But I can solve this system. I don't have M inverse anywhere. I didn't have to take the inverse of M. So if the system doesn't have an inverse, this path to solution works just as well. So even when there is a matrix that can't be inverted, this approach tells you how to do it. So the cool thing is that one of those equations then, if one of the eigenvalues is 0, what's it going to look like? It's going to look like x plus y or something equals 0. So it's going to tell you that there's not a unique solution. There's a whole set of solutions where if I gain a little x, I have to take away a little y, or if I gain a little y, I have to take away a little x. So the thing that the matrix inverse was messed up on was it can't handle this kind of system. But this solution path with the eigenvectors and eigenvalues is totally happy with it. And so what we're going to find out is that these kind of solutions are the unforced free modes of the system. So on the ocean surface, it's flat because gravity's pulling down on it. But if you put waves on top of it, they can propagate around and be totally happy. They don't have a forcing, they're just living there, free modes, bouncing around doing their thing. In the differential equations, that always comes from a 0 eigenvalue in the original set. So the forced modes will be associated with the part that's a matrix inverse, but the free modes will be associated with the part that has a 0 eigenvalue. And so we're going to see this over and over again in algebraic systems, vector calculus, and also differential equations. We'll keep coming back to the idea that 0 eigenvalues are really special ones. They tell you about free oscillations in the system. Does that sort of make sense? In some vague sense? But the simple part is, if I can't invert this matrix, I can make progress by examining this equation. That's the part that is the simple takeaway. And I can guarantee that if I can't invert that, one of the eigenvalues is going to be 0. That's what I mean by can't invert the determinant 0. So we're going to have a few equations that are of something form like this. Okay? I know this is sort of a crazy set of bizarre things to come through, but we'll keep seeing it over and over again in more context. Right now, you have the idea what an eigenvector is. You know it behaves like this: eigenvector, eigenvalue. We can construct this funny diagonal matrix. You've seen how to do that. And we're just going to see examples where that gets more and more useful. And then you'll start to have a sense as to why this is an important thing to do. The other thing I could have done is I could have gone the other way and written M equals C lambdas. I could have multiplied by C inverse on the other side. And this is cool because this is like a shorthand for M. Once I have the eigenvectors and I have the eigenvalues, I can tell you what M was. It's always that. I can build M from construction. So going through this whole process of eigenvectors and eigenvalues is all kind of like lost in the weeds of solving these equations. But this is a nice way of thinking about things. Yeah?
So you were saying earlier C times inverse C equals the identity matrix.
Mhm.
So would this be equivalent to saying M equals the lambda matrix, or is it not because of the order of?
Yeah, so this is saying that the lambda matrix in M's natural coordinate system, the coordinate system where the eigenvectors are the coordinate directions, the lambda matrix is M. So M in its compressed notation is the lambda matrix. But we also have to know what coordinate system that is, so that's why there are these C matrices that are projecting you in and out of that other basis. Yeah.
So like, for two matrices to be equal, strictly speaking, they can have different values, they just have to be the same operation.
Yeah, that's really a good question. What is a matrix? A matrix is what a matrix does, not the way it's written necessarily. So this is a complicated way of writing something. This is one, but I can guarantee through all the equations we've manipulated that if you multiply this by anything, and you multiply this by the same thing, you will get the same answer. So the fact that the operator of this matrix is written differently, but it still has the same answer whenever I operate it on something, means it is the same thing. The function is the same, even if the way of writing it is different. Which is kind of a, whatever. Okay. I'm pulling on this. We're going to look at some things and talk about linearity a little more before we go. Oh, don't have my doodad. Does anybody have one of those doodads for a USB-C? I can go run it and get it upstairs, but I forgot to bring it downstairs. SVGA, USB-C. I'll go grab one. You guys think that's good?
We have basis vectors, I love it.
Yeah, I think it's like, remember on 25, we're going with the X, Y thing, which is like IJ, and then we shifted over these. So like the eigenvalues. 1, 1, this is like 1, this is 1. Shift it over like what? From this one here. I guess that one stays the same. So you're going from x1 to u2, u1. Those are new axes? Yes. Because it's kind of like
This little doodad. Why is it every classroom in the world has the plug on the right and the computers always want it on the left? Okay. And it's looking for HDMI, which is not what I wanted to do. I wanted to look for.
No.
find the range here. I'll have to draw these by hand in a second if they don't come up. I think their definition of moment and mine are quite different. Maybe no connection. Try this one more time, then I'll just give up and draw it. Wants to do that. Boom, boom, boom. Still not working though. Yeah, stupid thing. Alright, well, I'm gonna draw it anyway. We'll switch and see if it comes up. I'm sure once I give it up, it will start working just fine. Okay. So, if I think of the global temperature changing, we drew that picture last time. That was like, back that way. If I think of the global temperature, what did it do as we were increasing the CO2? So I had time, and I had temperature. What does that figure look like? It goes up, and then maybe it overshoots, and then it kind of levels out somewhere. So, what do you think the forcing underneath this looks like? We talked about increasing the percentage of atmospheric carbon, CO2, by 1% per year up to about here, and then level off. So what does that look like then? That's saying that something like CO2 concentration went up and then leveled off in time. This one didn't have the overshoot. Remember, this was where we evaluated the transient climate response, was right where we had hit the doubling point of this. Okay. So, would you say that the response of the system to the CO2 is in some way linear? What do I mean by that?
If it were responding linearly, it would increase by a constant amount.
Yeah, so it couldn't have this hump, because this function would have to look like this function, right? If I multiplied by this by a number and it went something like this, then you could say it really was a linear response. there is actually, so how does the CO2 concentration, this is actually not really a plot of CO2 concentration, I'm cheating and telling you it is, but it's actually the log of the CO2 concentration. But how does the CO2 concentration depend on the emissions? So this year we burn this many fossil fuels. What happens to that stuff?
Some proportion of it is always CO2.
Some proportion ends up as CO2 and some gets like reabsorbed by trees and the oceans and silicate weathering and all this stuff, right? So but once we've stabilized CO2, whatever those absorptions and emissions are all balanced, right? So the net emissions over absorption is 0 to hold this stable. What does the net look like here?
More emissions.
More emissions. So the emissions curve looks something like emissions of carbon looks something like this, and it goes down to 0, net 0, at this moment, this TCR moment. So the figure I was going to show you is from the IPCC's 1.5 degree report, which shows you a couple of different versions of doing this. One that's really soon and fast, one that's farther off, and one is what if we just sustained emissions. And it tells you what the temperature response is. So let's do this. If I was not emitting so much in the past, what do you think the CO2 concentration would look like? If I had just half as much emissions.
With the slope they have?
Yeah, it wouldn't be increasing as fast. So it'd be something like this. Do you think the temperature would be as warm on this one as it is on that one? Probably not. Do you think that the slope, so you said the slope would be half, so there's some relationship between the slope here and the amount here. What kind of, and it seems like it's a linear relationship, but if I had said a quarter, you might have guessed that this was a quarter. If I had doubled it, you might have guessed the slope was doubled. So what kind of a relationship is that? If I take emissions times a factor equals the slope, what kind of a relationship is that? It's going to be a differential equation. It isn't yet because I'm still saying slope, but I'm saying slope is proportional to emissions. So what kind of a relationship is this? This is the kind of equations we've been talking about all week. This is a linear equation, but since that's a slope, I might choose instead to write that as dCO2 d time equals alpha times emissions. That's a differential equation. And it turns out that what sets the equilibrium climate sensitivity is the integral of this. So this part, once it settles out, is actually determining kind of where that guy settles out. And so I could write this instead as CO2 equals the integral of alpha times d time. And this object is actually proportional to the change in temperature after equilibration. So, okay, is this a linear equation? Maybe, maybe not. Is it taking the derivative of a linear thing? So what was our definition of linear? So a times x1 plus b times x2. A linear operation on that is equal to a linear x1 plus b linear x2. If L is d by dt, does it do that? Yeah, so differentiation is linear. So this is a linear algebraic equation. This is a linear ordinary differential equation. This is a linear integral equation. An integral is also a linear operator by that definition. So the fact that change in temperature is not instantaneously proportional to this year's emissions, we can't make it especially hot year by emitting now, but cares more about the cumulative emissions, doesn't mean the system is nonlinear. There is still a linear expression of this, but it's in linear differential relationship. So we're going to talk an awful lot about linear and nonlinear differential equations after the midterm, but I want to start warming us up to why we are spending so much time thinking about linear algebraic equations, because linear differential equations have a whole load of other stuff that we're going to be worried about. This is just pointing that out from a climate perspective, that that kind of system is going to be really helpful to think about. Okay? And then we'll be able to compare a little bit between the linear and the nonlinear differential equations that actually underlie the real system. And little humps like this are a sign of nonlinearities. We'll be able to think about that more precisely after the midterm.
I have one question.
Yes.
How many questions did you all of them write in the packet?
How many questions should there be? There should be 10.
Yeah, so that's the.
Yeah, it should be order 10 for 2 chapters. It should be order 10 from now on. It was half for the first week. And sometimes they might have multiple parts if the multiple parts are easy. Sometimes they'll just be one if they're kind of harder. Yeah.
Thank you.
And there are some lurking linear differential equations in the homework too, which you will see when you start seeing them, but they're just taking derivatives will be enough to figure them out. Okay, cool.